Let's take what we learned in the previous video about how to analyze where horizontal asymptotes are, and let's apply it to a couple of more complex functions that involve radicals and then also exponential functions. So let's take a look at the function g of x equal to 3x plus 2 in the numerator, and then in the denominator the square root of 4x squared plus 2. Well, for the end behavior, just like we did in the previous video where we kind of realized there's a shortcut laying there for us, for the end behavior, we can still just focus on the highest powers of x in the numerator and the denominator. And so if I do that, very similar to what we were doing in the previous video, I'm going to look first at the limit as x approaches infinity of g of x. For this particular example, I'm also going to look at what happens as x approaches negative infinity as well, because we get kind of an interesting result. Well, this idea right here is approximately equal to the limit as x approaches infinity. If I'm looking at the highest powers of x in both the numerator and the denominator, then really what takes control of the numerator is 3x, and what takes control of the denominator is the 4x squared. The plus 2 really loses control of this function, and so it is the square root of 4x squared. Now you might be looking at this and saying, great, that's 3x over 2x, call it 3/2 and we're done. The problem is we have one little definition that's floating around that's going to make things just a little bit more complicated for us. And that is the fact that we define the square root of x squared as being equal to the absolute value of x. In other words, if I say, what's the square root of 4, you tell me 2 because you are taking the positive value. However, negative 2 squared is in fact positive 4, but we use this definition to give us that singular answer. And so really right here, if I'm taking the square root of 4x squared, I don't get 2x, I get the absolute value of 2x. So if I look at the limit as x approaches infinity here of 3x over the absolute value of 2x, I do in fact get the x's to divide off, and then as x is growing infinitely positive, this is staying positive, this is obviously being forced positive because of the absolute value, and so this does in fact equal 3/2 like we thought it would. So because this statement right here is true, we can say that g of x has a horizontal asymptote at the line y equals 3/2. Now then, in this particular case, we also need to consider what happens as x approaches negative infinity of this particular function g of x. Well, I get the same idea. I'm approaching negative infinity of 3x over the square root of 4x squared. I can actually go right to this piece right here, 3x over the absolute value of 2x. And again, I'm going to get this behavior where my x's divide off, except now that I'm going towards negative infinity, this numerator is going to be approaching negative values, the denominator being forced positive. This right here is actually going to equal negative 3/2. And so I get a horizontal asymptote as I go out to infinity of 3/2, but as I go towards negative infinity, I have a horizontal asymptote of y equals negative 3/2. And I would encourage you to graph this function either in your calculator or looking at Desmos, and you'll actually see both of these horizontal asymptotes come true. The other thing that this function does is it actually crosses over these horizontal lines before kind of coming back to them as we start going towards infinity and negative infinity. So if you've ever had a horizontal asymptote described to you as a line that the function never crosses or never touches, that's not true for this particular function. So I would encourage you to take a look at the graph of this function and really verify why these two statements are true, and it kind of stemmed from this technicality here of how we define the square root of x squared. Let's take a look at another unique situation where it does require us to look at positive infinity and negative infinity. And so let's consider the function. We're going to throw some exponentials in there now. H of x equal to 2 to the x plus 6 divided by e to the x plus 2. Well, if I want to look at the limit as x approaches positive infinity of 2 to the x plus 6 divided by e to the x plus 2, again, I'm really looking at seeing what is taking over with this particular function. As x is growing infinitely large, 2 to the x grows really, really large. You know what exponential functions look like. E to the x, it also is growing really, really large. The fact that I'm adding 6 or that I'm adding 2 really doesn't have any impact as x is growing infinitely large. And so I can say, you know what, this is behaving at the end of its graph like the function 2 to the x over e to the x. Now we haven't really said much yet because as x grows infinitely large, both my numerator and denominator are also growing infinitely large. But if I look at this and I remember one of my properties of exponents from algebra, I've got 2 to the x, I've got e to the x, I can rewrite this and say that's the limit as x approaches infinity of the value 2 over e raised to the x power. And now I need to have an idea of where 2 over e is on my number line and think about what happens as I am raising it to large powers. The main thing I want to look at is I want to establish the fact that 2 over e is less than 1. And I want you to think about what happens when we raise values less than 1 to an exponent. So think about 1/2. 1/2 to the 1 power is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. As I am taking this to larger and larger powers of x for any value less than 1, then I can say that the limit as x approaches infinity of this particular function, which we called h of x, is getting really close to 0 because this right here, 2 over e, is less than 1. If I had a value that was larger than 1, like if you think about 3 to the x, it grows unbounded. But because I had a value less than 1, raising it to an exponent, this value ends up approaching 0. That right there is my definition. So I can say h of x has a horizontal asymptote at the line y equals 0. Just like we saw in the previous example, I also want to look at the limit as x approaches negative infinity of my function h of x. All right, so now let's think about what happens as x grows infinitely small. Think about what 2 to the x does as it goes towards negative infinity. The value that it's approaching is actually 0. And you can think about that if you remember just kind of what the graph of an exponential function looked like. As you go towards positive infinity, yeah, it's shooting way up and growing unbounded. But as I go to the left all the way, that function approaches 0. And the same is true for e to the x. So if these two values, as x is growing towards negative infinity, are both going to 0, then the part of the function that's actually in control now is 6 over 2. So I can say this is approximately equal to the limit as x approaches negative infinity of not h over x. Let's go ahead and call it what we wanted to call it, which was 6 over 2. And that's going to be a constant value for us. Well, the limit as x approaches negative infinity of 6 over 2 is the same thing. The limit as x approaches negative infinity of 3, and we know the limits of constants are the constants. So as I approach negative infinity, this function right here is approaching 3. So I also have a horizontal asymptote at y equals 3. And again, just like the previous one, I would encourage you to graph this and really verify this behavior. But analytically, this is what's happening that gives us those horizontal asymptotes.